Cobwebbing is a very cool and useful way to understand dynamics in biology. I want to talk about cobwebbing, but before I do that, I want to step back a little bit. And I want to talk about a model that we can use for drug concentration where a drug is being applied to a patient. And I want to initially analyze this using methods that we've already used previously. And then I want to pick up the same problem using cobwebbing and show how that gives us new insight. And so the problem itself is from week 2 of the course. Here, there's a patient who is being administered a drug on a daily basis, and then part of the drug washes out every day. And so we use the quantity Cn+1 to be the concentration of the drug in the bloodstream after the injection on the nth day. So we're assuming that the injection of the drug is right at the end of the day. And now we're going to assume that 30% of the drug remains in the bloodstream the next day, and that the injection itself raises the concentration by 0.2 milligrams per milliliter. For this scenario, we can have an equation of the form shown right here. Cn+1 is 0.3 times Cn, that's at 30% from the previous day, plus the new amount, which is 0.2. And so we're going to look at this problem. And initially we're going to look at it using the tools of week 2 before moving on to using cobwebbing. And so to start with, as warm-up problems and review, we're going to do 4 things. Okay. Calculate the first 4 terms for the sequence. And we're going to assume in the first scenario that the patient starts with 0 milligrams per milliliter in their blood. That C0 is equal to 0. And in the second scenario, we're going to assume that they start off with 1 milligram per milliliter. After we calculate the first 4 terms for the sequence, we're going to plot them. And then we're going to actually write down the solution to this equation using a formula from week 2 of the course. And then after writing down the solution, we're going to look at the limit as n goes to infinity of C sub n. And this will allow us to determine what happens to the blood concentration of the drug in the patient after many days. So let's start with 1. And so we'll start with the case C0 is equal to 0. And then we write C1 is equal to 0.3 times C0 plus 0.2, and that will be 0.3 times 0 plus 0.2, which will be 0.2. C2 is 0.3 times C1, which is 0.2 plus 0.2, which will be 0.26. Continuing, C3 is 0.3 times the value we just calculated, 0.26, plus 0.2. And if you put that on your calculator, that's 0.278. Let's do one more, C4, and it's 0.3 times 0.278 plus 0.2, and that turns out to be 0.283. Okay, and we could continue further if we wanted to. Let's try it now with the case where C0 is equal to 1. C1 is 0.3 times 1 plus 0.2, which is equal to 0.5. C2 is 0.3 times 0.5 plus 0.2, which is equal to 0.35. C3 is equal to 0.3 times 0.35 plus 0.2, which is 0.309. And C4 is equal to 0.3 times 0.309 plus 0.2, which is 0.292. Okay, we've got an interesting pattern going on here. In the first case, we started with C naught as 0, and it gradually increased and approached 0.283 by the fourth day. When we start with a higher level, C naught is equal to 1, it's decreasing, and it looks like it's approaching a similar number. So when we plot these sequences, we can use the axes. On the horizontal axis will be n, or the day, and on the vertical axis will be C sub n, or the concentration of the drug. And the first sequence starts at 0, and then it moves up to 0.2 in day 1, and then to 0.26 in day 2, and then 0.278, and then 0.283. If we start from above, the second sequence starts at 1, and then it goes to a half in the first day, and then 0.35 the next day, and then 0.309, and then 0.292. Okay, so you see a pattern here. Both of these sequences seem to be approaching a value which is approximately 0.28. The next thing we're asked to do is to solve the sequence. So let's think back. If we have a sequence of the following form, Bn plus 1 is Rbn plus C, with B naught is equal to A, then we know that the solution to this problem from a previous video is Bn is equal to R to the n times A plus C times 1 minus R to the n over 1 minus R. And so we can use this result here. We have to correlate this equation with this one over here, and so choose R is equal to 0.3, because that's the multiplier. Choose C is equal to 0.2, because that's what's being added each time. And choose A is equal to C0. And C0 will either equal 0 or equal 1. And so look at the case C0 is equal to 0. Then we have Cn is equal to 0.3, that's R, to the nth power times C naught, that's A, and C naught is equal to 0, plus C 0.2 times 1 minus 0.3 to the nth power divided by 1 minus 0.3. Okay, so this term goes to 0, and so Cn is 0.2 into 1 minus 0.3 to the n divided by 0.7. If we choose the case C naught is equal to 1, we have Cn is 0.3 to the n times C naught plus 0.2 into 1 minus 0.3 to the n over 1 minus 0.3. And so this equals 0.3 to the n plus 0.2 over 0.7 times 1 minus 0.3 to the n. So we've actually written down a solution, an explicit solution for the sequence. And so given any day n, we can calculate the drug concentration for either of the two cases. The last thing we're asked to do, item 4, is to determine the limit as n goes to infinity of these two solutions. So let's start again with the case c naught is equal to 0, and then we have the limit as n goes to infinity of Cn will be the limit as n goes to infinity of 0.2 over 0.7, 1 minus 0.3 to the n, and that's equal to 0.2 over 0.7 into 1 minus the limit as n goes to infinity, 0.3 to the n. And because 0.3 is less than 1, this is going to go to 0, and so this will equal 2 over 7, which is approximately 0.28. That was the value we found on the graph as the horizontal asymptote. And if we start with the case c naught is equal to 1, we have the limit as n goes to infinity of Cn is equal to the limit as n goes to infinity of 0.3 to the n plus 0.2 over 0.7 into 1 minus 0.3 to the n, and put brackets around the whole thing. And so this will be, this term here will go to 0, and this term here will go to 0. And so we'll have 0.2 over 0.7, which is 2/7 for the answer here as well. And so notice both of these sequences are approaching the same value, 2/7, as n goes to infinity.